So what did we have last hour? We have this coin flip, right? Heads or tails. Heads or tails, and now we repeat it n times. Then we constructed this estimator for the probability of heads, right? So this is Q, which is a function of the parameter. And this is just basically very naively given by the frequency of the heads, right? So K divided by N. And then we were wondering, okay, but now since we can estimate Q, can we estimate? Can we track back to estimate B, because Q is a function of B, and we know the dependence of Q on B. Yes, and we just give this estimator. It's just, well, very intuitive. Just take the estimator of Q and apply the inverse function of our physical model. So the inverse of this Q of B. Okay, and indeed we just seen that it's kind of converges to an unbiased estimator symptotically, and at least it gives a good estimate for large N. And now we want to compute the mean squared error of this estimator, right? So the mean squared error of the estimator, by definition, is just the expected value of the estimator minus the true value squared. Okay, so in our case, if you just write it down, this is sum of our binomial distribution for the number of heads, k from 0 to n, so B, remember B is Q minus 1, right? This is Q minus 1 of Q. Applied to the estimator, so applied to K over N minus B squared. Now again, we actually will take the limit here and large, and we'll only expand the thing. So because you see what happens is that when N is large, this distribution here, basically, so actually the distribution of the frequency, so the estimator of Q, the distribution of the estimator of Q here, Q, inside the thing, it really just becomes peaked around a certain value, Q of B, right? Here. So if we, and what we're computing here, right, is really just the convolution of this distribution here with this function, with the inverse function here, QB, so along this line sort of. So what we really care about is really only how this function behaves around the central value. Okay. So in other words, because P here is very sharp, the only thing we care is how this function here behaves around its mean. Right? So we'll just use the fact, so then we'll just kind of use up in this limit, we'll use approximation for actual array. That will just expand, so expand, go to the limit and expand this function Q minus 1 of chi over N around the mean value Q hat equal to Q over N. Right? Because again, this is almost a delta function. And of course, this is just Q minus 1 of Q hat, so of the average, right? So Q minus 1 of Q plus D Q minus 1 of Q divided by K. You should actually replace it with, well, over D, dk, so to say, right? Of at the same point at K over N equal to Q. Okay.
Maybe, sorry.
Yes, sorry.
Write in black because it's much harder to see the red.
I should write in black. Okay, so.
Thank you.
So the only thing, so right, you got it, no? So we get this. This is the expect. So this is the variance of the thing here. So the evolution of the distribution which is picked around our mean value Q. And to compute it in the limit n goes to infinity, we will just, this is a constant, we will just expand this around the central value of this peak. So now around this peak, right? So now we write the same in black. So Q minus 1 as any function, right? We just use it. This thing is just Q minus 1 at Q, right? Because the average of the distribution is precisely Q plus D Q minus 1 over D Q over N. Again, at the value Q. Okay, times Q minus K over N. So the first order, right? Now, the next thing I want to use is, you see here we have a derivative, so we have this function Q of B. Let me just draw it here again, bigger. So we have our function B, Q of B, look. And what we want actually is the derivative of Q minus 1 of B and of the inverse function, right? But of course, you know that this thing here. So this is just the derivative of this inverse function at some point, right? But of course, you know that, so if you have like just two functions, like y of x, then dy over dx, right? This is just equal to 1 over dx over dy. In other words, the derivative of the inverse function is just 1 over the derivative of the function. Yes, I mean, this is not, so we can just rewrite it as being is equal to, again, the inverse function of q1, this is b. So this thing is just b plus 1 over q prime of b. At this true value, so this is q, the inverse of at this point. So times, what it should be? Times deviation from the true value. So this would be k over n minus q. Minus q, yes. Right? So the first order deviation, right? Okay, so write it down, plug it here, and we get in the limit. We get to the limit that this is just given by sum of q equals 0, p of q, k, so the distribution, and here we get our b, plus the first order expansion, which is 1 minus q prime of b, times k over n, minus q, right? Minus b squared. So we see that again, in the first order, of course, the b disappears, so the only thing we're left with is this thing. Okay, in other words, if I write it again, we just get this derivative now can be factored out. It's just the derivative of our model, so this doesn't depend on any measurement. So we get 1 over k prime of b squared times, well, this thing. And this thing is just the variance of our estimator, of the estimator of q. So it's just the mean squared error of the estimator of q. So it's a sum of k equals 0, n of k over n minus q squared times p of kn, and this we just computed previously. It's just the variance of the Gaussian, right? So to summarize, we find that the mean squared error of the thing is 1 over q prime square. The variance was what, if I remember correctly, the variance of this estimator, this was p, sorry, no, it was not p, q, q1 minus q over n, right? This is what we just computed before. Indeed, so this is kind of the variance of the thing, and this goes down as 1 over n. Good, so now we managed to express in the asymptotic limit how the mean squared error of our coin estimator depends on this value q. So you see, it's really just asymptotically, as you should expect, it's really only a property of kind of q and of the derivative, because we really can, the estimator will converge. So the sensitivity to changes in b, as you might expect, is inversely proportional to the slope here, right? The bigger is the slope, so the bigger the q changes with b, the better you can estimate the field asymptotically, which is very, very, very natural. Just one thing, I will actually rewrite it in another basis, because now we want to make the fish information appear here. So to do this, we just have, how does this go? Write it like this, 1 over n times 1 over q prime squared over p. Why am I writing p all the time? Q prime squared over q1 minus q, okay. And this is 1 over n times the inverse of q prime squared over q plus q prime squared over 1 minus q minus 1, right? Is it true? So if I sum the fractions like this, I'll get, so 1 over q plus 1 over 1 minus q, I just get q times q 1 minus q plus 1 minus q, q times 1 minus q, right? So indeed, this thing is just given by 1 over q times 1 minus q, okay? So these two expressions are the same, this is minus 1, all right? Why I'm writing this? Because you might think, oh, yeah, what are you doing? Are you writing something? But actually, this is because it's important for the next thing. So what we have is mean squared error is given by 1 over n, the Fisher information of the distribution Q of B, and 1 minus Q of B. Okay. Well, it's not, so just it's a bit tricky because this should be a curly f, not to confuse with the fidelity. And so let's write like a curly f like this. And the Fisher information is of such a distribution is really given by sum of. So in our case, it's just Q prime Q squared plus 1 minus Q prime 1 minus Q. And the square is here. Right? This is the expression we have here. Derivative of this squared. Of course, if you derive Q and you derive 1 minus Q, the derivative squared is the same. Just derivative of Q. So, summary of this small example, we've seen that kind of there is a natural estimator to construct for this value of the parameter. And moreover, I managed to get this mean squared error asymptotically. So when n is large, this will be given by 1 over n times this Fisher information of this probability distribution of P of heads, right? And I will not write it down again because this is what we are going to discuss next. So this will be next chapter, Fisher information. Fisher information, it's just first let me give a definition. The definition of definition. So for a curve, in the space of probabilities, in the space of probabilities, again P of B, right? Which is equal to this probability of outcomes conditional on B. The Fisher information at B, the Fisher information at B is, we'll write like this, f of P and B. So, and this is equal to sum. Now we considered coins before, and I'll just write exactly the same formula, but with any number of outcomes. So for k equal 1, let's say to n, this will be a probability of k, the derivative of the probability of k, right, squared, derived by the probability of k at b. Okay, this is just the definition, which we're going to use repeatedly now. Okay. So basically what we just had is that for the coin toss with n repetitions, we've seen that the mean squared error we constructed at the end converges to the value 1 over n over the Fisher information of this distribution of outcomes, which is also a curve depending on the parameter b. Good? So what shall we do now? So first I think let me give you another definition for the Fisher, and then we see what is its geometrical interpretation. Another definition is typically what people use in statistics. So if you open Wikipedia on Fisher information, you won't see this definition, but you will see another one. So let me just give it to you. And it will be also, it's actually just formally related to this one, but somehow people like to write it this way. So we have let's keep it here. So Fisher information of P of B. This is just sum of P prime K, pk squared, right? Where the derivative, of course, is with respect to the parameter. So, okay, so another definition, this was the first definition. Second definition is that we can define the score function, yeah? So remember, we had, the story is as follows. We have our parameter B, right? The parameter B gives us an outcome X, the outcome of the measurement, and the outcome of the measurement gives us an estimator of the field B. And here we know precisely this function here. This is our model. And well, we also know this function. This is what we construct here, right? So we don't know it, but we construct it in a way that it's a good estimator So now we can define another random variable, which is the score. Okay, so define the score. So the score is given by the score S. It's also a random variable, so it's also now we have the score of x, and the score of x is just really, so it's a bit of a weird definition. The score of x is given by a log of p of x b, the derivative with respect to b. Okay. So, right. So again, this is a random variable because this thing is something. So when we observe x, we just compute it. Basically, we know this function p, so we can also compute the derivative of p, right? Since we have the function, we also compute the log of x. So we just compute this function and we plug in the value of x. So kind of for a particular realization, for a particular measurement outcome, the value of this s will just be, well, I take x and I plug it in this function and I get it. Now the point is that why it's nice is that because the fish information is actually just the expected value of the score of this random variable s. Okay. So this is another definition. So we just say f of p, and this is very easy to see, of b is equal to the expected value of s of x squared. Okay. Now how to see it? Well, just take this definition and derive things. So what do we get? And we get the following thing. So okay, score here. Let me write it down here. This is log d log of p of x conditional on b. This is the score of x head divided by db. So keep it here. And well, just look at it. So the expected value of s squared. This is sum of the probability of the outcome k. So this is so k is the value of x, right? For our n outcomes. Well, times this times s of k squared, and s of k squared is the derivative of the log, right? So this you can just rewrite the score as so derivative of the log is one over the function, right? So the derivative of log is just p of x b times p prime of x b, right? This is what the score is. So if I just plug it back in here, again, this is a function of x. Yeah. If I plug this back in here, I just get sum of k equal 1 to n of p of k b times p prime of k b times p of k b squared. Obviously, you see that the square here disappears, so this is just k of 1n p of kb squared, the derivative squared divided by, right? And yes, this is just some expressions here. The derivative of the probability for the case outcome squared divided by the probability of the case outcome, right? So this is just to say that we can also see the fish information as the expected value of some variable, some random variable, which is defined as a function of the measured outcome. Good. So we have this weird quantity fish information, and we're going to hear more about it in the next lectures, also for the quantum case. Now, what does it mean? So, can we interpret it in some way, some nice way? And in fact, yes, we can. So this will be a connection to. So we can connect it to fidelity. Connection to fidelity. Okay, so let me draw again our curve of stuff, our curve of probability distribution. So this probability distribution space, simplex. Here, there is our p of b, right? Our vector of probabilities, so the probability of outcomes defined there. And of course, we also seen that we defined already on the space some distances. So we defined the trace distance and we defined the fidelity, which is not a distance which kind of quantifies how close two distributions are. And in fact, the claim is here is that the fish information f of p at b is nothing more. So let me just first write the claim that 8 times, I think, limit when db goes to 0 of the fidelity between the probability at b. So 1 minus the fidelity Okay, do you see this? Yes. So the claim is the efficient information actually just quantifies how fast the fidelity of the states of the probabilities drop when B changes, right? So in other words, if this is true, and we are going to prove it right now, this has a very simple interpretation, right? So we have this curve, parametric curve, which is our physical model of the setup in the space of probabilities, and the Fish information just really quantifies kind of the speed of evolution along this as given by the fidelity. Yes. Yeah. So let's just prove it. So yes, that's a claim, and now we want to prove it. So then I'll really there is not so much. Okay. So it was a good idea to keep things kind of, but the board is too small, so I'll just erase it and start again. So let's do it. Let's just take the fidelity of two neighboring distributions. Okay, so I have the fidelity is, remember we have a curve PB here. Again, I draw it again once more. I have a curve in probability space, and the fidelity of PB and PB prime. This is just equal, if you remember, by sum of pk of b, pk of b prime square root, right? This was the definition we gave in the second lecture or third lecture, something like this. So now I will write a nicer kind of way to see it is just write it as overlap of two vectors. So we'll just see the sum of rk of b, rk of b prime, right? Whereas the vectors then adjust that, so we'll define a vector r of b. So p of b is just equal to the square root p of b, right? Right? So I just take the square root of each probability. So in other words, if p is, so this is p1, p2, p3, p lives, so the sum of p is equal to 1, so it lives on the simplex. For this vector r, it will be normalized for the squares. So the sum of the squares of rk is equal to 1. So in other words, now we can just take the simplex, and in the R space, it will just be given to the quadrant of a sphere, right? So this is R3, R2, R1, and the curve will be kind of on the surface of the sphere. Simply because this is nice, because it's just R of B times R of B prime. So the fidelity is just the scalar product of these two vectors, which are not probability vectors, but normalized vectors on the unit sphere. Good. So take this, expand it in the first order, and on first orders on dB. Yes. So well, nothing very crazy. So R of B prime is actually B plus dB. We want to expand it. So B prime is equal to B plus a small deviation. So basically, this is just R of B plus what? Plus, well, yeah, R prime of B dB plus R double prime of B and dB squared of 2. Yes? Yes. So the fidelity between P of B and P of B plus dB then is just again sum of K of R K of B. Now I'll just plug this expression there. So first thing is just gives us a square here, right? Because the first order R is just R of B prime is just equal to RB, plus second order is, no, it's okay, I don't know if do you? No, it doesn't just write it. One more line, so to write it explicitly. So we have RK of B times RK of B plus R prime K of B dB plus R double prime K of B dB squared over 2. All right? Let me just write it now. So first thing is that sum of K, RK of B plus sum of K, RK prime of B This is the second order term, dv, and this the final one is plus sum of k, rk prime, rk double prime, dv square over 2. Okay? Well, a little bit long, lengthy, but very simple. So you directly, first you see, of course, that the first term, the zero order is just 1. Yeah? This is the sum of rk squared, which is precisely the sum of pk's, so the sum of probabilities. So this is normalized. The first thing we see directly is that sum of rk squared is just equal to 1. All right? Next, we look on the second term. The second term is sum of k, rk prime. I dropped the dv for the moment. Well, you see that this is actually just given by the derivative of rk squared prime 1/2, right? So if you derive this thing, you get rk squared, right? I just get 2 rk prime. In other words, this is also just, you can put the derivative outside, so this is just the derivative of the sum of k of rk squared 1/2 prime, and this is just 1/2. So this thing is always given to 1. So the derivative is 0 because it's normalized. This is 0. So this is 1, this is 0. We're just left with 2 terms. We're just left with the last term. This is the one we care about. Oh, very good. So in other words, now we get the fidelity of P, the probability distribution B, and probability distribution of B plus dV. This is equal by 1 plus 1/2 sum of 1, so dV square, 1/2 sum of rk double prime. Yes. Now let's just recall what rk is. Rk is the square root, so rk is just the square root of pk. Good? So let's derive it. So it means that rk is prime is equal to 1/2 over pk prime, square root of pk. Correct? I guess yes. Right, so it's 1. Yeah. Okay, and then what we need is a second derivative, so it's even more lengthy. The second derivative is then, well, 1/2, and I have to derive this expression. And to derive this expression, so we use this pk, right? So, you know, the derivative of a over b is a prime b minus b prime a divided by b square, right? The high school formula. So this is pk double prime times square root of pk minus pk prime square root of pk prime divided by pk. Finally, this is, I have to just derive this guy here. So this is pk double prime 1/2 square root of pk minus, again, this derivative here is 1/2 pk prime square. Okay, sorry for this, it's long, but here we go. This is rk double prime. So I just plug it back in this expression. Good. Just plug it back in this expression, and what we get is, well, 1 plus dv square over 2, sum of k of, I put the 1/2 in front, so this is 1/4. And then we get simply, rk here is square root of pk, so I multiply by this, so we get pk double prime pk, right, square root times square, minus 1/2 pk prime squared times the square divided by the square, so nothing, divided by pk divided by pk. Yes. Okay. Again, there are 2 terms, but as you will see, one of them is good. So what is this thing now? And this thing is precisely what we want. So it's just 1 minus dv square over 8 times sum of pk prime square over pk, right? What is this? Fish information. But there's another term, but this one will be 0. I don't remember why, but let's see. Plus, yeah, well, it's simple. So this term is just plus db square over 4 sum of pk double prime, pk over pk. Well, so pk disappears. And again, same trick. We just put the derivative outside of the sum. The sum is 1, so this is 0. Good. So a bit lengthy, but we are there. So the fidelity now, remember the definition. So this is the fish information of P and B, right? So what we get is that the fish information, so the fidelity is of, yes, so this expression here, the substitutability of fidelity is equal to 1 minus dB square over 8 times the fish information of the distribution at B. All right. Let me just summarize it. Well, so okay, finally what we wanted is the definition of a Fisher, so we just pass it on the other side, divide by dB square, and you get the 8. So finally we met, so we prove what we wanted, right? So in other words, now we prove that from this thing, we get Fisher information of P of B is equal to, well, the limit when dB goes to 0, of course, of 8 times, because it was 1 over 8, 1 minus f of precisely the drop of fidelity Yes. Nice. So indeed, we have this very nice geometrical interpretation now of our fish information. It's actually just the speed of how fast, just quantify the speed of how fast the fidelity of the state drops when we go along this curve now in an infinitesimal step. You see that basically it's dB squared because the fidelity is really only grows as in the second order, right? The first order, as we just saw, is zero, with zero contribution. Now, well, maybe nice thing, even more simple, is that if you remember these vectors, right? So this R, so we have this curve in R space. Then you remember maybe in the second lecture we defined the angle. So the angle A of two probabilities P of B and P of B prime. This was just given by arc cos of the fidelity between them. P of B prime, right? So in other words, it's really the angle between two vectors which correspond to the probabilities, right? Because this is the fidelity is the overlap of the vectors. So I'm taking the arc cos to just give you the cosine of the angle between them. And then if you just plug here this expansion, so the fidelity just you put it, so this thing is 1 minus 8 times the fish information times dB. Well, basically what you get is that this thing, well, I'm not going to give you the proof, it's quite straightforward. You just have to develop the arc cos to the first order, just so I don't get you the wrong. This is basically fish information of PB times dB, but there is a factor of some factor like 1/2 or something. Yes, 1/2. Right, so it's even, so it's, you can see it, so fish information is basically the speed of drop of fidelity, but it also like just quantifies how fast the angle. So if you instead of probabilities, you consider now the square root of probabilities, which are vectors on the unit sphere. Fish information just quantifies how fast the angle increases when you go away, right? So it's a very simple geometrical thing actually, right? Good. Now we wonder, but okay, this is very nice, all this fish information. We've seen an example where it was the case, but how can I use it? So why should I care about this fish information? Except this is a small example which we had with the coin. Well, but actually there is a very important theorem in estimation theory, which precisely allows you to relate the Fisher information to the error you do. Again, this is what we're going to do now, and this is a Kramer-Rao bound. Kramer-Rao bound. Okay, and the Kramer-Rao bound says the following things. So suppose I have again my parametric model, so the measurement probability which depends on the parameter, yes, in the simplex. And I get an unbiased estimator. So for any unbiased estimator, for any unbiased estimator, V of X, right? So this is a measurement, X is a measurement outcome. We have the mean squared error of this estimator is lower bounded, so it cannot, so the mean squared, the error will always be bigger than 1 divided by the Fisher information of the probability, right? Okay. So it's not only kind of a geometrical thing with Fisher information, but it also has a very nice interpretation in terms of how well you can estimate the parameter. At least it's a lower bound, and we'll then see that kind of in the limit of many repetitions, it's also attainable. So it's not just lower bound, but it's also attainable, right? So this is really a very kind of nice statement, Kramer-Rao bound. If you look, I don't know, if you start reading a paper on quantum metrology, you'll typically, people will claim something around this. This is Fisher information is important for this reason. So let's just prove it now. So we have 10 minutes. I think it's just enough time to prove it, or maybe. So, okay, so how to prove it? Now we got our statement. Well, sorry guys. Let me turn this off. To prove it, just again remind our things. We have our true value, right? Then with the probability x of b, we obtain the measurement outcome is a random variable, and then from this measurement outcome we can get our estimator. But we also defined the score previously, right? The score is another random variable which depends on the estimator. So now we have these two random variables. So let's to prove the Kramer bound. We'll just play with these two random variables. Yes. First thing is, remember the score. It was well, let me just like it here because it's not an estimator. Typically, just put heads on estimator. So the score is just d over dv of log of p of x b. Okay. So in other words, we'll just say that we can write it as p of x d prime divided by p of x b. So first, the expected value of the score, right? This is sum of p of xb times s of x. So this is sum of p of xb times p prime of xb times p of xb. So you see that it's 0, right? Because it's the expected value of a normal of the same thing. You just put the probability of the prime out of the sum, and this is just 1 prime equals 0. So one thing we have is that the square, of course, one thing we know already on these certain variables is that S has 0 mean. Okay? So S has 0 mean. Just write it down. So S has 0 mean. So, in addition, we know that B is an unbiased estimator. So the mean of B minus B is also equal to 0, right? So the mean of B is precisely given by this thing. Okay? Well, now we consider the following thing. We have our two random variables. We just look on the product of their variances. Okay? So let's look on the product of their variances. So we take S square, because the variance of S is really just 0, so the variance is the second one, times B minus B square variance, right? expected values. This is nice because we have here all the things we want, right? Remember, this is the mean square error, so this is the Fish information, as we've seen. This the expected value of the score is the Fish information, so this is P of B times this is the mean squared error of B. Okay, so if you manage to lower bound this quantity, we will lower bound this, and then we can pass the Fish information on the other side, and we actually this is how we'll get the Kramer outbound. So let's see what this thing is. There's a sum of k of pk, pk of b times s of k, right, square, times sum of k of pk of b, b minus b square of k, of course, here, right? So we can actually see this as a scalar product. Each of these guys, we can see it as a scalar product of vectors. So let's define the following vector: square root of pk, sk, right, times square root of pk, sk. So we take just an n vector with elements. We see that the scalar product of these two vectors is precisely given by the sum, right? Times this is this thing. Okay, times the scalar product of the same vectors we define here. So here we'll have, again, just vectors which are pk and b, k hat minus b. Okay, again, n1 to n vector times this one. Nice. So, in other words, what we have here is just the product of the norms of two vectors. And now, you might be surprised, but we are going to use Cauchy-Schwarz again, right? So remember Cauchy-Schwarz, it was telling us that the norm of two vectors, this guy and this guy, this thing is always bigger or equal than their overlap. X times y, I guess, norm, yes. Wait a second. Norm, that's the square root, yes, exactly. Right, it's an absolute value. Which is a trivial statement for vectors, right? So here we just read it. So we use it already for like operators and image product. For vectors, it's really trivial. It's kind of very intuitive. So yeah, so in other words, the thing which we get, which was mean squared error of the estimator, b, times the Fish information of this probability curve is bigger or equal than the overlap of these two vectors. And the overlap of these two vectors is, scalar product of these two vectors is really just sum of k, right, this times this, so of pk of b times s of k times b of k minus b. Yes, now, what is this quantity? Well, we open the brackets, so this is equal to, first term is sum of p of k of b, s of k, b hat of k, this is what we're interested about, minus, actually, for the other term we just put b out, b, and then we get just sum of p of k, b, s of k, but s, the score, has zero mean, so this is zero, right? The only thing we care about is this. Okay, now let's plug it in. The formula for s of k, and the formula for s of k is just, you remember this derivative of the log, right? So s of k is p of k b prime divided by p of k of b, and this thing is equal to sum of p of k of b, p prime of k of b divided by p of k of b times b of k. Okay, so this goes away, we get sum of yes. Now let me just check the very last step. What did I do this? Yeah, well, yes. So, yes, you see the only thing which here, this is, what is this? This is just a function of k. So the estimator, right? The estimator is a function which only depends on the outcome. It doesn't depend on the true value because we don't know the true value, right? It's only defined on k. So it has no dependence on b. In other words, actually, we can just put this derivative outside because the only thing here which depends on the true value b is the probability of outcomes. The estimator is constructed on the whole space for all possible values b, or actually at least around 1, but it cannot directly depend on b because that's what we try to recover. Yes, so now it's clear now what happened because this thing, the derivative of course with respect to b. So now this thing is just the expected value of the estimator, right? So this thing here is precisely b prime. So this is just because the estimator is unbiased. This is actually b prime, and this is equal to 1. Okay. Right. So with this, we get basically all the thing here. This first product of the two variances of these random variables, which is our estimator and the score, is bigger than 1. Or simply rearranging the terms, we get precisely Kramer of 1. Bigger or equal to 1 over ms mean squared error of, yes, those were answers. This is how we want it. So the error of the estimator cannot exceed the Fisher information. Right? So the Fisher information is really a very central quantity there. Okay, so it tells you how well you can estimate the quantity. Yes, so this is about time. Now, actually, I wanted to tell you a bit more, but I guess I'll just tell Nikki to get some exercise there. So one thing which is important here to observe is that so what happens here is that we have just one measurement, right, which is described by this probability P of KB, but we can consider the scenario now. We will repeat it again. It's just we did with the coin. Now then we won't have a probability distribution PK of B, single one, but we'll have like a direct product of this probability distribution, right? So we just have a series of random variables which correspond to independent runs of the same experiment. Yes? And then you might ask, so now if you look on this global data, how is the Fisher information for independent runs goes? And it turns out that it's actually very simple, and you can, like, it's really a one-line problem, but maybe you can even decide that if you have like, so this probability is, you know, we have like many of these probabilities for many independent trials, right? Then the Fisher information is just equal to n, so n times here, and the Fisher information of the single one. I guess we'll put it in the side. Yeah? In other words, if you consider now the same scenario, but now I don't do just one estimation run, but I do many, right? Then the Fisher information of the global thing will just go as n. So in many repetitions, in other words, in many repetitions, this additivity of Fisher information will just tell you that the mean squared error with n repetitions is directly bounded by the Fisher information of the global variable of the global data, and this is n times this story here, right? So we'll just have the n, as we had before for the coin. Yes, the coin we had the n in front. Moreover, for the coin, we've seen that this thing is attainable because we constructed this estimator where we actually get an equality here. And in fact, for large n, it's always attainable. It doesn't matter if there's two outcomes, many outcomes. The point we used is that for a coin, this binomial distribution and then becomes a Gaussian. Well, if you had many outcomes, it will be a multinomial, right, in general. But the multinomial will kind of also become sort of a multivariate Gaussian in a larger space, right? But actually, the same thing you can do at the same expansion with derivatives, you will get the same formula for things. So Kramer bound is a Lapper bound, but it turns out that with what we showed basically is that if n goes large, then it's also attainable, right? So it is just a lower bound on the error, but if you repeat many times, it's also an attainable lower bound. Yes. So that's kind of the two things you should know about it for the future. All right. So again, as before, now we have this before we had this fidelity rate distance, which measure how far states are in this probability simplex, or probabilities are in this probability simplex. Now we define this Fisher information, which is basically just the speed of evolution in the simplex. But again, as before, they had a very nice interpretation in terms of estimation. Now the Fisher information also has a very nice interpretation in terms of estimation. Yes, it really gives you the bounds user error you're doing estimating the parameter. Next time, actually, we will take this formulas and we'll bring it to the quantum scenario where we don't have probability distributions, but we rather have quantum states. Like, so it will be like now a parametric curve in the space of quantum states, yes? And we will try to make the same, tell the same story there. And actually, yeah, it works pretty similar, but with different, very different tools too, because it's now matrices, right? Yeah, so I guess that's it.